So next up we have Shaun Rawson from Harvard Medical School. So Shaun and I sat next to each other during our PhDs, so I'm greatly interested to see what he's been up to in the last couple of years since I haven't seen him.
All right. Just let me know if South Africa has any problems with the audio, by the way. So I'm going to talk to you today about how we have our setup at Harvard Medical School at the moment, and in particular, how we're set up so we can rapidly identify and evaluate good data sets in our microscope. So like John said, it's vitally important that we use our microscope time well. There's no point us collecting huge volumes of terrible data on suboptimal data sets. And most of that goes back to grid preparation, and in the end, actually, we find that we end up sending most of our users back to the bench to re-optimize at that point. So I realize this is a European meeting, so you probably don't realize the setup we have at Harvard, so I'll just give a very, very brief overview. So we're set up with 2 Titan Krioses and 1 Talos Arctica microscope. All of these are equipped with K3 cameras. That has had some issues of its own, but I won't come into that here. And that was a result of a major renovation work and a collaboration between 3 major Boston-based medical schools and hospitals. So Harvard Medical School, the Dana-Farber Cancer Institute, Boston Children's Hospital, and Mass General Hospital. I'm not only employed by Harvard Medical School, though. The other strand that I work with is a group called SB Grid. Now, some of you in the audience will be familiar with what SB Grid do, and they work as a software consortium supplying software for structural biologists all around the world. Now, the beauty of SB Grid, and what we do mostly as an outward-facing group, is we provide software stacks that are curated, tested, and I like to think just work. So rather than having a postdoc or a person in your lab who maintains your software and tries to keep every version updated and working with every other version, we handle all of that in-house. We test all of our software installations on multiple OSs and make sure it all works together. So for the end user, for the scientist and the researcher, they don't have to think about their software installs. And that's great because no postdoc wants to spend 30% of their time curating a bash RC file that they don't quite know how it works. They inherited from the postdoc who came before them, and they don't know what half of it does, but they know they can't comment out some of the lines. So we try to minimize that. To put that in perspective of how complex this ecosystem is, currently we have roughly 400 titles in our software stack. And these update at a rate of roughly 30 new titles a year, and maybe 5 to 10 updates to those titles every single month. Now again, that's beyond the scope of what a postdoc should be expected to keep on top of in your lab. So for that, it's actually a really powerful feature, and for EM in particular, recently this has got even worse, or better, as you might say. So traditionally SB Grid has underpinned structural biology, and that has meant crystallography. But in the last kind of 2-3 years, over 30% of our new software updates every single month have been EM software. So you can see in this plot that actually just towards the end of last year, we've updated a couple of software packages like motion correction or cryo-EM multiple times in the space of 2 to 3 months to make sure we're on top of all the new bug releases, all the new features. And that's a tremendously powerful thing. So this is kind of the backbone of structural biology and computing at Harvard Medical School. So we use this software tree to underpin all of our computation. Along with that, we specialize in kind of pre-processing and inline on-the-fly pipelines, and how we tie that with our logging and monitoring tools so we can provide rapid information to our facility staff and our users at all times. Is that right? Cool. So for that, we have a fairly large dedicated setup just in computational hardware in order to make this go as smoothly as possible. So we're not a national facility, we're not resourced in the same way that EBIC and Diamond are for this, but for the user base that we have a fairly decent setup for our computational needs. And this is expanding all the time, so we're not even a third provisioned at the moment in terms of our overall budget and space. And this is all underpinned by fast networking, a huge amount of cooling actually, so we have 3 times as much cooling in our server room as is required to run our server room, because one of those coolers dies, that's okay. 2 of those coolers die, it could happen on a short period of time, and then all hell breaks loose. And you might notice that we have very little storage provisioned, and that's something I'm going to touch again on towards the end of the talk, because honestly, we didn't want to deal with user storage. So, you're all aware of the EM pipeline and how you go from your noisy, low-contrast image to your beautiful, hopefully 3D structure, which tells you all your new, interesting biological insight. And as biologists, that's what you care about. For a lot of you, you don't care about the steps in between, how they work, what they do. You just want them to work and you want them to be painless. So that's where we come in. So a lot of these steps are quite repetitive. They require very little expertise and very little user input. So we want to make those automatic where we can, and when we can't automate them or remove them, we want to make them simple. So to do this, we need an automatic pipeline which takes you from the data from the microscope all the way as far as we can go towards your final structure. At the same time, we need to keep track of all the data, where it's moving, different points, and then that can also feed into a monitoring system so we know what we're doing is right. Now, of course, this automation comes at the cost of flexibility. So we have a system that will work for most cases, and a user with little to no command line experience or EM experience can come, start running the software, and they will get an output. The downside of that is we trade off flexibility. So if an advanced user comes and they have a particular set of parameters that they always use, we can't really accommodate that easily without increasing the complexity of the system. And that's something I will come back to. So with that in mind, we want as few variables as possible to pass on to the user, because we deal with a lot of medics, a lot of cell biologists. We want them to just get to their results quick. And at the same time, it has to handle all of the file transfer behind the scenes, all of the file moving steps from various servers, from the K3 onto storage, and onto the computational pipeline. So for this, we use the rely-on pipeline as kind of the backbone of this. So at this point, I really have to stop to thank Shaun and his team, as well as CCP-EM, for developing this. You might notice the GUI I'm showing is a little different from the one that Colin and others have shown, largely because because it's written in Python and explicitly made for this, I've taken this, I've modified it, taken out the parts that didn't work for our setup, added in new modules, and changed the way we pick particles, for example. So the pipeline focuses on mainly the first kind of 4 steps of the structural biology pipeline, which is motion correction, CTF, particle picking, 2D classification. We do actually go all the way to 3D classification, but I'm not going to talk about that much today, because in honesty, the success rate is variable at best, shall we say. And that's something I think we need to improve on in the future, definitely. So, as others have spoke about, particularly yesterday, the rate of data collection has gone through the roof in the last year since the introduction of this multi-hole imaging modality from Wim Hagen. So we're collecting somewhere in the region of an image every 10 seconds on our K3, which is roughly 350 images an hour. So 5,000 images for an overnight data collection. This means we have users who in a single data collection session are collecting upwards of 1,500 images. Sorry, 15,000 images. So to do that, we have to go fast. And that requires quite a large amount of computational resource. So for this, just to keep up with the motion correction, we're using 6 GPUs that do nothing but dedicated motion correction all of the time. Now this, again, as with everything in life, is a trade-off between speed and thoroughness. So we decided we'd go for thoroughness, actually. We could go a lot faster and use less computational resource, but in that case what we found was most of our users were taking the data back to their home lab, and they were rerunning motion correction anyway, which kind of rendered the entire point of us doing it for them quickly pointless. So we had to go back to using what I would consider, and I'd happy to hear otherwise, the standard parameters for motion correction. So full patching, 5-5 patches, full dose weighting, etc. Coupled to that, we need a reliable set of quality metrics, so we use CTF Find to generate our per micrograph statistics. And despite being CPU, this is fast enough for our needs. Now, where we diverge from the rely-on pipeline as built by CCP-EM and Shaun's group is in the particle picking. So the default in the rely-on pipeline is using the Laplacian of Gaussian followed by template-based picking. And If your grids are really good, like I'm imagining the grids that this was tested with at the LMB, it works fantastically. I found the grids that some of our users brought for data collection were not quite so good. So we needed a more robust pipeline that could deal better with the amount of junk that some of our users brought. So for this, we use cryo-EM, which is a software package written by Forsten from Dortmund, who I believe is in the audience somewhere. So thank you very much for that. And this is, actually, it really made this system work for us by adopting this picking software. We have a single model that we can adopt, and it will pick, I would say, everything that comes from our facility, it will pick pretty well. We'll never do every micrograph that comes perfectly, and we don't aim to. What we want to do is do good enough for everything. When we find a test case that it doesn't work, cryo-EM is a machine learning-based picker, so if something doesn't work, I can ask the PI in question for some of that data, we retrain the model, and then the next time that PI comes to collect data on a related protein, we get a better result. Now, why do we want to go fast? The reason we want to go fast is to quickly eliminate things from our microscope that shouldn't be there. So in this case, we had a group of cell biologists who were collecting data, and they got really excited. They didn't quite know what their protein was meant to look like in the microscope, but they started seeing these classes appear within kind of minutes of starting their data collection. And they could see this clear symmetry appear in their object. Now, a lot of you in the audience probably already recognize this, if you're experienced in EM. But what in fact they had is they'd successfully purified cryo-EM. That was not their protein of interest. Unfortunate. So what that allowed them to do was see this quickly, even build a rough kind of 3D model within hours of their data collection starting, and then they could go, oh, what have I done? And they could go back to their lab book, back to their gels, realize that they hadn't purified it maybe as well as they thought. They could stop their data collection and then save valuable microscope time, which was then freed up for other users in the facility. The flip side of this is you can also see if an experiment has worked very rapidly. So in this case, we had a group that had got the structure of a fairly small complex to a reasonable resolution, and they wanted to start adding binding partners into this to see where the binding sites were, if these binding partners truly did bind as expected, and what kind of stoichiometries. So at the top, you can see the apo structure of this particle, and then within probably a couple of hours of their data collection starting, they got these classes where there was a clear extra density on the edge of their particle. Now this allowed them to get biological insights from their EM pretty much instantly. They could see their binding partner was bound. Just from the 2D class, they could see where on the complex it was bound, so they could start to work out some of the biology behind this and see if it made sense with the literature. And you might be able to see that in these classes, the binding partner is actually quite a lot weaker than the surrounding densities. So what this told them is that they either had incomplete binding, they had different binding modes, or that the binding was fairly flexible and heterogeneous. So at this point, as I mentioned, they had two options. They either go back to the bench and try and find a way to stabilize this connection, or, as they did in this case, collect an enormous amount of data to try and computationally fix this flexibility and heterogeneity. It's not necessarily the best option. They're probably better served by going back to the bench. So, with this, we want to tie this all into a monitoring system. So we want to do two phases of monitoring. We want to track our usage statistics, so we know how well our microscopes are used at any given time, whether we can spot trends that are forming, so is our microscope getting better, getting worse, and we also want to catch problems with our microscopes very quickly. Now, these should be extremely stable instruments, but in truth, they're not, especially with the newer K3 detectors. We still have unexpected downtime windows. So we want to be able to catch this quick. So for this, we use a data aggregation tool called Splunk. And as you can see, it's in dark mode because everything is made better by putting it into dark mode. So this allows us to capture data on every single data collection that comes through our facility. So in whatever month this was, we collected 12 data sets while we were in our commissioning phase. We know how much data each microscope collected, how long each microscope collected for. We can work out the average resolutions, the average drifts, for every data collection that comes through. And this allows us to quickly track usage and see, are our users using super resolution data collection, counted data collection, and this lets us inform our training moving forward. So if none of our users choose to use super resolution collection mode, then we know that we should focus our training towards counting mode data collections. And this allows the facility staff to make better use of their time and then better use of the microscope time. The other side of this is we want to see we want to catch problems quickly. So for this, we monitor a series of different quality metrics via generally CTF-based metrics. And we also monitor just whether or not the microscope is running. And if any of these fail, certain fairly simple numerical checks, all of the facility staff receive an email at 3 in the morning telling them that the microscope has suddenly stopped collecting. I don't think the facility staff particularly love this, but it is very useful to maximizing our instrument uptime. So this is our kind of typical at-a-glance dashboard that you can see for our microscopes that are operating at any time. So this is probably a fairly normal day, actually. Most of the microscopes are operating all the time, and they're reasonable. The exact values don't really matter so much in themselves. It's more if the trend is stable and there are no huge spikes. So we have this set with certain thresholds. So at this point here, where everything looks like it's going wrong, all of our facility staff receive an email. They can remotely connect to our systems and they can check what's going on. We can then dig down into this in a little bit more detail. So in real time, we can plot several CTF parameters, so CTF max resolution, focus parameters, astigmatism, and figure of merit. Again, the exact values of these aren't so important. It's more noticing aberrations and differences from the kind of normal operation. So this, again, is a fairly normal data collection. Everything's proceeding along. You can see a large pause in the middle where the users stop their data collection in order to add a bunch more acquisition areas before restarting it again overnight. So this is what we want to see most of the time. And then we have days which aren't quite so good. So this is when we were testing our faceplate for the very first time. And as you can see, over time the astigmatism gets worse and worse and worse and worse and worse. And this is every time we've changed faceplate position, the astigmatism would get worse. So we noticed this, we're able to quickly go back, although if you can see the time, it actually says it's 3 in the morning, so we didn't go back in this case. We can quickly go back, we can fix the acquisition script, and then we can make sure that data collection proceeds better from that point onwards. Now, I said we have a relatively small amount of storage on site, so in the region of 350, 360 terabytes. Now, if we're collecting 5,000 images per microscope per day, you can probably do the math to realize that that's not enough storage for the amount of data that we collect. In fact, even though we've only just officially opened to our user base, even in our commissioning period, we've collected close to 300 terabytes of data. So that's not happening. So we, as a facility, decided to offload the responsibility for our data storage and data handling onto the users themselves. So we will store a copy of our users' data locally for a short period of time, say a few weeks to a month. And then, once we've checked with the user that they have their data and they've signed their life away saying we realize our data will be deleted, we just wipe their data automatically. The onus for data storage is entirely on the member labs. One of the reasons we did this is because we are a multi-user facility. We have the labs that collect our data do not process against our file systems. And frankly, we just didn't have the resource or the will to become data curators and keep on top of every micrograph that's been collected. Saying that, we do still want to keep on top of the information about every micrograph that's collected. So while we don't store raw data, and that is the responsibility of each lab group, we collect all the metadata for every collection. Now, Empire and EMDB are wonderful things, and the deposition systems have got better, but I don't think anybody enjoys doing an EMDB submission. There's still lots of fields. There's lots of fields where, you don't know what the value is, probably. So you just kind of guess. As Gerard alluded to, there's a lot of, whatever. Now, We want to minimize that. We want to make it as easy as possible for our user base. We also want to eliminate the situation where a collaborator emails you and says, oh, we're going to publish this data set you collected 2 years ago. Can you just give me all the information about it? And then you go back to your lab book and go, oh, 2 years ago, okay. We want to take that out of our postdocs and PI's hands so they have an easily searchable database where they can just put in their name of their data collection, the microscope they collected on, or basically any field they want to search on, and just copy and paste out the information directly into submission forms, just to make people's lives as easy as possible. Now, where do we want to go next with this pipeline? Ideally, we want to get to a beamline-like scenario where you collect your raw data, and by the time your data collection is even finished, you already have a rough, well, in crystallography, MTZ file. We would love to be able to get a refined structure, even if it's not a perfect one automatically. We're not there yet. It does work for test specimens like the beloved apoferritin. And I would like to tell you that we just put this data set through the pipeline, selected out the best class, refined it, and put it in Buccaneer. Unfortunately, the hand was wrong. But other than that, we effectively did. So it works for simple systems, and I think it's going to work better for more complex systems over time. But for that, we need a better way of selecting out good data without human input. We need to be able to do classification and pick out the correct classes, probably by some kind of machine learning-based approach, I would imagine, to make this work. Now, the final point is, where do we stand on quality of our results automatically versus how easy they are for a lay user, a naive user? I don't think we have the balance of that right, but I'm not sure where the balance for that stands. We want everyone who comes to our facility to be able to get the best data with the minimal difficulty, but we also want to give them the flexibility. And the more options we give people, the more problems that's going to generate in the system and for the naive users. So I don't know where that point is, and I'd be very happy to know where other people think that point should be drawn. So finally, I'd just like to thank all of the people involved at the Harvard Medical School and their setup there, both on the facility side, who've set up the facility and keep it running day to day, and all of the SB Grid team who maintain not just our software stack, they also do a huge amount of hardware behind the scenes, and they keep all of our servers running and everything running smoothly. And with that, I'll just take any questions.
Thanks, Shaun, for a really interesting talk. Does anyone have any questions?
Based on your experience so far, do you have an emerging understanding of which steps in the process you are confident are close to being performed as well automatically as by users, and which steps desperately need the input from machine learning people?
So at the moment, I would say our particle picking is pretty good. If we train our model to our particular system, I would say it performs as well or better than a human. If we take a generally trained model, which has been trained across a range of different proteins, it probably performs better than a naive human. Whether it performs as well as an expert, I couldn't say. I guess it would depend very much on the expert. When it comes to steps later down the pipeline, then 2D class selection is really the problem. How you select the well-aligning particles to feed into the later steps is still where, at the moment, a human can open it, within 4 seconds, pick out all the good classes and be done. There aren't good metrics. You can't really use even angular accuracy, accuracy of translations. There are no good metrics that will work for every system. The ones that work well for good data tend to fail for really terrible data. And I think that's where the machine learning community could really help us, because I'm not a machine learning person, but it feels like that should be a solvable problem just by looking at enough different 2D classes and being able to work out what looks good in general versus what is junk.
Any other questions? No? Okay, so we'd just like to thank Shaun and all of our speakers from this morning's session. Okay, so just before I let everybody go for lunch, I'd just like to say it's an absolute pleasure to be here at this year's CCP-EM, and thank you very much to Tom, Colin and Martin for giving John and I the opportunity to put together a programme of speakers this year. Fantastic to have all of you speakers here. Thank you so much for agreeing to come and speak. And I must say that this year I'm especially grateful to be at CCP-EM because it means that I'm not on a bicycle anymore. Because for those of you who don't know, myself and a number of other people from University of Leeds cycled between every Titan Cryos and JL Grand Arm in the country to be here. So if you all don't mind, Neil and I are just going to show you a few sort of pictures and videos and tell you a little bit about the ride. So just going to plug the laptop in. So the first question that most people ask me when they talk about the cryocycle was, were you drunk? And the answer was, when you came up with the idea, and the answer is yes. So Neil's PhD student, Dan Hurdis, had his Viva back in February now. And during that, everyone had far too many drinks. And Neil said, do you know what, I really fancy doing another big bike ride. Maybe we should go between all the cryoses in the UK. And I went, that's a great idea, we should definitely do that. And then the critical mistake was made, Neil texted his wife saying that, we were going to do this bike ride and we were going to raise money for a charity, which Neil is going to tell you about a little bit about in a minute. And at that point, it really had to happen at that point. That was kind of the decision made. So the journey was just over 700 miles, 705 miles. Took us between Glasgow, Leeds, Oxford, London, Cambridge, Leicester, and then finishing up yesterday at about 12:30, thankfully, just in time for the EBIC user meeting. So the UK doesn't have any Alps or anything equivalent to that, but when we totted up all of the hills that we climbed during the ride, then the overall height climb that we went was higher than Mount Everest. So, and believe me, I can feel that in my legs. So really know that we did that. So just go to the next one. So we had an absolutely fantastic team from Leeds coming and doing this bike ride. So myself, Neil and Ollie, a PhD student, cycled the whole route. And I've got to say that Ollie is an absolute machine because one of his knees gave out very, very early on in the ride. But Ollie does a lot of weightlifting, he's quite a powerful guy, so just decided to do most of those 700 miles with just one leg, which, as you can see, has resulted in kind of a slight, what I like to call a pigeon-style kind of cycling, and Neil said he looked like a pirate, so yeah.
And I should say this is genuinely not hammed up. This is Hay Road for about 400 miles.
Yeah. So that was, so absolutely astonishing effort from Ollie. And obviously Neil as well. So Neil is... So Neil is a very experienced long-distance cyclist, but I have to point out that Neil had what can only be described as severe man flu for approximately half of the ride, and was doing some of the toughest sections on about a third lung capacity, and was producing more snot than I've ever seen a human being produce in my life. So, he did an absolutely sterling job of leading the team on the bike ride. And
it's called a cold, not man flu.
And I should add that Neil was also an absolute hero because he had 2 grant applications. He doesn't want me to say this, but he had 2 grant applications that were due in the middle of the cryocycle ride. So he was working incredibly hard right up to the beginning of the ride to get those in on time. So
if anyone happens to review one of those grants, it would be great if I could remember. So we also had Molly cycled all the way from Glasgow to London, again, despite having 2 only partially functioning knees before we'd even began. And she was absolutely incredible, the whole way. She really was an effort of mind over matter. So I don't even know where she is. She's over there. So yeah, absolute hero, Molly. So other names we have on there, Sophie Hesketh. She rode from Glasgow to Leeds. Sophie could have merrily ridden the whole thing with her one hand tied behind her back and a blindfold, but unfortunately she had to go to Utrecht for a conference, so she had a get out of jail free card on that one. And then we had David, Rodrigo and Laura join us from Banbury/London. Much welcome arrival of fresh legs and cream eggs. So thank you, Laura. Much appreciated. Dave was a special guest for about 30 miles, and Josh as well also came from
from Leeds, all the way. This is out. The names are out of sync. And Josh came all the way from Leeds right down into London. Again, battling some serious knee problems. You notice that knees are a continuing theme of bad health on this one. So luckily, the EM facility's on the ground floor, so I don't have to get up any stairs. Amazing effort from all of the Leeds team. It's fantastic, and we were incredibly grateful that so many people from the cryo-EM community also came and joined us on our bike ride. So we had loads of people from loads of different sites around the UK joining us for parts of the ride, providing much welcome extra kind of conversation, motivation, and in some cases very large holes in the air for me to cycle behind when I was feeling quite tired. So thank you so much to everybody who joined us. It was really, really fantastic to have you along, including Tom and Colin from CCP-EM. One of my highlights was that Tom brought his two little ones in the trailer and was pulling them along, and he could still, with the trailer, with his two children, run circles around me. So yeah, some seriously pro cycling there, Tom. Cool. So, although we had lots of fun, the UK is a very beautiful place, and being on a bike is a great way to see it. It wasn't all fun and games. There was a lot of suffering. So Neil, when we signed up, said you have to do visible suffering.
So this is called Fleet Moss. This is the highest paved road in Yorkshire, and climbing it on a bike looks like this.
I was not happy.
This is the very top. It's 20%.
I genuinely thought I was going to die.
Okay. So both Becky and Molly got to the very top in one go. It's really outstanding effort.
Yeah, I'm not doing that again. I'm not doing that again.
The point of the ride, of course, was Krios's and Grand Arms.
Yeah.
And we really did it.
So we visited 20 microscopes across the UK, from Scotland down to London and everything in between. And I just want to say a massive, massive thank you to everyone, all of those sites who came and let us in on weekends, fed us amazing food, was just generally so supportive. The electron microscopy community in the UK is a wonderful community to work in. I love coming to CCP-EM because there's so many friendly faces that we get to see, but really when you're on a bike and you've just been cycling for about 4 hours straight and somebody gives you a cheese sandwich, you're just like, I love you. This is amazing. So we were incredibly grateful for all of the support from every single site, so thank you so much for everybody who came and gave us support on that one.
And a special mention to Laurie, who gave me a Scotch egg. Laurie here.
Fantastic. So I think now we're just going to finish off, and Neil's just going to say a couple of words about why we put ourselves through this, quite frankly, stupid idea.
So we rode for a charity called IJM, which is the world's largest charity working to end modern slavery. It's a charity that's very close to my heart and my wife's heart, and I'm going to show you a video which tells you what this charity does, and I'll just say one word after it.
So this is the target establishment. First suspect, you or our victims. Remember, if there's any absurd dangerous situation, move yourself to a position. We saw about 1,200 little kids in fed out that they were in fact trafficked and they were in fact slaves. These little kids are on this boat. They are not fed. They are abused beyond imagination. This is a doll. Whenever something like this comes, I imagine in my mind that blood is small.
We have operations all over the world rescuing people from slavery. Because today there are criminals who abuse children, sell girls, and force families into slavery. Criminals expect no one to defend them.
Pareho po tayong mga tao. Hindi po tayo bagay or hayop na pwedeng gamitin lang sa pansarili.
But today, there are thousands of people gathering to seek justice for those in slavery. We are a group of lawyers, counselors, activists, and supporters. We are called International Justice Mission. And together, we form the largest international anti-slavery organization in the world. But slavery won't come to an end until criminals know they can't get away with it. So we partner with local police to arrest and prosecute criminals. This sends a message to slave owners. We will not go away. We stay with the survivors until they are healed, until they are free.
Natulungan po ako ng IJM sa pamamagitan po na sa Facebook, sa pagtulong po nila na ma-overcome ko po yung fear.
Each year we rescue thousands of slaves and protect millions around the world. We are transforming how justice systems protect their citizens. To those who are still enslaved, we promise to find you. We will get you home to your families so you can have the freedom you deserve.
So that's why we did it, because we wanted to be the people who stand up, and we wanted all of you guys to be able to contribute and stand up with us. So thank you.